Hello everyone. In this video we are going to study about instruction set, addressing mode and basic assembly programs. So instruction set, CPU uses many register to store temporary data. In AVR there is only one data type, that is 8-bit register, starts from D0 to D7. So these are the 8-bit data and there are total 32 GPR, means general purpose register. So all are of 8-bit register. So 32 general purpose register, which is from R0 to R31. So these are the 32 general purpose register in AVR. All are of 8-bit register. Next, to understand instruction set, registers, and we will see register and operands. So RD, which stands for destination register in a register file. Then RR, which stands for source register in register file. R, result after instruction is executed. K stands for constant data. Then small k, which stands for constant address. B stands for bit in register file or input output register. S stands for bit in status register. XYZ, they are indirect address register. X is from R27, R26. Then Y is R28, R29, and Z is R30 to 31. And A stands for input output location address, where Q stands for displacement for direct addressing. First instruction, load immediate. So LDI instruction copies 8-bit data into GPR register, that is general purpose register. So load an 8-bit constant directly to register from 16 to 31. Now we cannot copy any register from R0 to R15. We can copy from R16 to 31. So operation, so here K stands for the constant value. So the constant value get loaded into RD, that is RD stands for destination register in register file. Then this is the syntax for LDI, LDI RDK, where RD is from 16 to 31, means we can use general purpose register from R16 to R31, and the value of K between 0 to 255, and then program counter will get incremented by 1. This is the instruction LDI R20, 0x25. 0x25, 0x stand for hex value, and this 25. So here this 25 get loaded into R20. Next, LDS, load direct from data space. So operation, this is operation. This K stands for the address, and that address get loaded to RD, that is destination register. So syntax is LDS RD comma K. So this K is nothing but the address, and the value of RD from 0 to 31. Now we can use R0 to R31, all 32 general purpose register in this particular instruction, and the value of K from 0 to 65535, 65,535, and then program counter will incremented by 2 in this instruction. So this is the instruction LDS R5 comma 0x200. That means the contents of location at 200 will get loaded into R5 register. LDS R0 0x300. Now look at the contents of location 300 will get loaded to R0, and here R1. So see here, this are the general purpose register from R0 to R31. This R0 to R31, this other general purpose register, and here internal SRAM is there, that is a location. So here first instruction LDS R0 comma 0x300, that means this 300, the contents of here location 300 gets loaded to R0 here, LDS 300, and the contents of location 30, whatever the contents here 0, suppose here 0x25 is there. So this value 25 get loaded to R1, and R1 become R1 will become 0x25. Okay, so this is a load direct from data space, LDS. Next instruction, add. So this is ADD, which is stands for add without carry. So add to register without the C flag and place the result in destination register RD. So this is the operation. RD get added with RR, and all the result will get stored in RD only. Then syntax, this is syntax, add RD RR, where value of RD from 0 to 31 and R also 0 to 31. So next program counter will get incremented by 1 for this instruction. Next we will see one example. See here, LDI R20 comma 0x35. That means 0x35 gets loaded to R20. Then LDI load immediate R21 with 0x15. So 0x15 get loaded to R21, and then we have to add these two registers. So add R220 comma R21. So R20 will become R20 plus R21. So the addition of these two will get stored in R20. So this is add without carry. Next instruction is add with carry, that is ADC. So we have to add with carry. So add to register and the contents of C flag, and place the result in destination register, that is RD. So here RD will become RD plus RR plus C flag, that is carry. So syntax is ADC, RD, and RR. Again, RD from D is from 0 to 31, and here RR is also from 0 to 31. So we can use any general purpose register from 0 to 31, and program counter will incremented by 1 for this instruction. We will see one example. So here again, see that example, R20, which means LDI load immediate R20 with 0x25. That means 0x25 hex value will get loaded into R20. Then 0x15 get loaded into R21, and then add with carry. Now here R20 will become R20 plus R21 plus C. If the carry flag generated, that carry is also get added into this R20. So this is add with carry instruction. Next, STS, which stands for store direct to data space. Store one byte from a register to data space. Operation, we have to store any contents of R into the particular location, that stands for K. Then syntax STS K RR, where again here R from 0 to 32. Then we will see one example, STS 0x230, that is 230, R25. That means the contents of R20 is stored to the location of 0x230. LDI load immediate R20 with 0x55. That means 0x55 get loaded to R20, and we have to store the contents of R20 at the location of 200. So we will use STS 0x200 R20. That means R20 is now R20 is 0x55. So at the location 0x200, 0x55 get loaded to this particular location. Next, in this is a load and input output location to register. This is also called as input instruction. Load the data from input output space, or we can say the port timer configuration register, into register RD in the register file. Operation, so whatever the input output get loaded to RD in syntax is in RDA, where RD is D from 0 to 31. We can use any register from general purpose register from 0 to 31, and the value of A will from 0 to 63, and the program counter will incremented by 1 for this instruction. Next is out. This is called output also. Out to store the register to input output location. So store data from register RR in the register file to input output space, that is port timer configuration register, etc. Then operation RR get loaded or stored in input output space. Then syntax out a comma rr, r is from 0 to 31 and the value of a from 0 to 63, and program counter will incremented by 1. Now we will see one example, or we can say the program state the contents of R20 and R21 and data memory location 0x20 after the following instruction or program. This is the program. So here LDI, that means load immediate. So here R20 get loaded by with 5. Then again load immediate R21 with 2. So the R21 get loaded with 2. Addition of R20 and 21. So add R21 to 20. Then again add, and now this is the instruction without carry. Okay, add without carry. So without carry we have to add, again add R21 to R20, and then sts save this whatever the contents of R20, load that or restore that contents to location 0x 20. So we will see after first instruction. This is my first instruction, LDI R25. So in R25 gets loaded. For second instruction 2 gets loaded to R21. Then after addition of 2, 5 plus 2, so R20 become 7 and R21 will be same as it is 2. Then again here add, next instruction is add R20 with R21. So what is R20 now? It's 7 and R21 is 2. So add 7 plus 2, it will be 9. 9 and R21 will be same 2. Then store this data R20 into location. So this location 0x 20, at this location 9, whatever the result in R20, now R20 is 9, so 9 get loaded to R20. So after the following program at location 0x 120, what is the value, 9 gets loaded to that particular location. Next instruction is move, which stands for copy register. So this instruction makes a copy of one register into another. So the source register RR is left unchanged while the destination register RD is loaded with the copy of RR. So here RR gets loaded to RD and RR will be unchanged, means whatever the data in RR, it will be as it is, and RD is get replaced by the value of RR. This is the instruction move. Syntax move RD RR, where RD is from 0 to 31 and R is from 0 to 31, and program counter will be incremented by 1. Here see move R15 comma R16. This is the syntax or example. Now we have to first load R15 with some data or R16 with some data, and then we can use this move instruction to move the contents of R16 to R15. So here we have to use LDI instruction to copy or to load some data in R15 or R16. Next, subtract without carry, SQB. So here subtract two register and place the result in destination register, that is RD. So here RD will get the result of this subtraction, RD minus RR will get stored in RD. This is the syntax sub RD comma RR, where D is from 0 to 31 and R is from 0 to 31. So any general purpose register from 0 to 31 we can use, and program counter will be incremented by 1. This is LDI instruction, LDI R20 comma 0x25. That means the value 25 value immediate 25 value get loaded into R20. Then LDI R21 15 0x15, that means 0x15 get loaded to R20, and then subtract R20, that means R20 is equals to R20 minus R21. So whatever the data, whatever the result subtraction of these two numbers get loaded into R20. Then subtract immediate. So that is SUBI, that is subtract immediate, subtract a register, and a constant, and the place the result in destination RD. Now here, uh, this instruction is working on the register from R16 to R31. Then operation RD minus K, this immediate value, whatever the value, this is a constant number, so the constant number get subtracted from RD, and the data will be stored in RD. Subtract immediate RD comma K. So D is from 16 to 31, and K is from 0 to 55, and the program counter will be incremented by 1. So here see, our LDI R16 comma 0x25, that means this 25 get loaded to R16, and load immediate R17, R17 data of 0x15 get loaded to R17, subtract R16 R17. This is the subtract instruction. SUB, we can use SUB I. Okay, now use this data R17. So here I'm gonna write R17. So the contents of R17 will get subtracted by this value 0x15. So this is the example of SUBI instruction. So whatever the data in R17, so here see, R17 is again loaded by 15, and I have subtracted this with 17. That means the result will, R17 will become 0. So this is subtract immediate. Then these are the instructions with two registers, which uses two register. Add, that means add, that is addition, RD RR. So add RD and RR, then add with carry, then adding, these are the arithmetic and logical operators which works on two registers, addition, subtraction, or multiplication. Then we can say adding, or then here SBC, that is subtract RR from RD from with carry, without carry. So these are the some instructions which uses two registers. These are the some instructions which uses two registers. Then these are the some instructions which uses only one register. Clear, increment, decrement, complement. Then one's complement, negative means two's complement, rotate left, rotate right. Then shift to left, shift to right. Then swapping of nibbles. So this use only one registers. This instructions uses only one register. We will see one example or one program to toggle the input output register of port B. 0x55 get loaded to R20. So R20 become 0x55, that is load immediate. Then out, port B in, this is output register. Here the port B act as a output port. So here out, port B R20. So this R20 get loaded to port B. Now port B become, here the value of port B will be 0x50 5. Then load immediate R21 to 0x AA. So here this AA gets loaded to 21, and then that R20, the value of or contents of R20 get loaded to port B by using out instruction. Out port B comma R21. Now this port B become 0x AA. Now to toggle port, see, we know that it is 8-bit register. To toggle this, first it will be 0 1 0 1 0 1 0 1 0 1, and the next time it will be 0 1 0 1 0 1 0 1 0. So the value of this is 55 or A. So here hex value, this is the hex value, 0x stands for hex value. So we are toggling it, but this program is only for one time toggle. Now for continuous toggling, C program to toggle the input output register of port B by now we can use a different instruction also, that is complement once complement also. So this is LDI R20 0x55, that means 0x55 get loaded to R20, then out this the contents of R20, that is 0x55 get loaded to port B, then complement of R20. Now whatever the data is there, it is 055, so complement this 055, it will be complement means 1 to 0 and 0 to 1, so complement this bits, so it will and it will be automatically become 0x AA, and then send this data to port B, out port B R20. So the contents of R20 will get loaded to port B. So we can use both this way also, and the another way by using complementary instruction. And we will see one program to toggle input output register of port B continuously. C programming, embedded C, we use while one loop for continuation or forever loop, infinite loop, while one loop, and we can use for loop also without giving the statements inside. So here this is the first LDI instruction is used, that means LDI R20 comma 0x55 means the contents 0x55 get loaded to R20, so R20 will become 0x55, then this 55 get loaded to port B, so out instruction is used, out port B comma R20, that means port B become 55. Now complement this R20, so R20 becomes 0xAA. Now load this contents of R20 to port B by using out instruction, out port B comma R20, that means port B become AA. Now for continuation, we will use one jump instruction, and we'll give the label to where we have to jump. So here this is the label. Now now the value of R20 is AA. Now complement R20, so it will become again 55. Then load this 55 to next instruction is out port B R20, so R20 become 0x55. Load this 55 to port B, then again jump to this L here to this instruction. Now what is the contents of R20? R20 is 0x55, complement again, it will become 0xAA, then this AA get loaded to port B by using this instruction. So here this is the forever loop. Next, program to get data from pin B and send it to input output register of port C. Now we have to take the contents of pin B, and that we have to send to port C. So here this is the program. See, input in R20 comma pin B means the contents of pin B get loaded to R20, then this R20 we have to send this data to port C, so we will use out instruction, out port C comma R20, that means whatever the contents of pin B get loaded to R20, and that R20 get loaded to port C, and here jump instruction is used L. So for continuous process, we will use this jump instruction, and this L is label, and this L label here. So this particular loop will be forever loop, or we can say infinite loop. Jump. Now we will see one example, show the status of zero flag. Now this is the this is the program. We have to show the status of zero flag. Now here first instruction is LDI R20 comma 4, that means R20 will become 4, load immediate, so the 4 get loaded to R20, so R20 will become 4. Then DEC, this is decrement of instruction, decrement of R20, so it get decremented by 1, so R20 will become 4 minus 1 will be 3, then decrement, again decrement, then 3 minus 2 it will become 3 minus 1 it will become 2, then decrement R20, then 2 minus 1, it will be 1, then again decrement, so it will become 0. So what is the 0 flag? See here, we will see, uh, after first instruction R20 will become 4, then 0 flag will be 0, because here in R20 there is some value, that is it is non-zero, therefore 0 flag will be 0. Then decrement R20 will become 3, and 0 flag, here it is also, here it is non-zero, so here 0 flag will be 0. Then R20, for next instruction R20 will be equals to 2, and this is 0 flag is 0, decrement by 1, then here R20 become 1, again 0 flag is 0. Now after this instruction decrement R20, now R20 becomes 0, so the 0 flag gets 1, because the value of R20 becomes 0, so the 0 flag is generated, or it will become 1. So this is the status of 0 flag after the this instructions. Okay, so we will see the next example. Show the status of C, H and Z flag after the addition of 0x38 and 0x2f in the following instruction. So this is the instruction LDI R16 comma 0x38, that means 0x38 get added loaded to R16, then R17 loaded with 0x2f, and then addition of this two. So here addition of 338 and 2f, 8, this will be 0001, and for 3 it will be 1100. Then f means 1111111, and 2 is 0100. So add this numbers, here see, 0 1 will 1, then 0 1 1, 0 plus 1 1, 1 plus 1 0, but the carry is generated between the half bits. Okay, so here carry, so half carry will become 1, because there is a carry from D3 to D4. Okay, here this is D3, D0, D1, D2, and this is D3. So carry is generated from D3 to D4. So here half carry will become 1. Next status of half carry is 1. Next 1 1, it will be 0, but the carry is generated, and 0 0 will become, okay, 0. Then 1 1 0, again carry is there, then 0 1, it will be 1, then 1 0, it will be 1 1 0 will be 1, and 0 0 will be 0. Now here at the D7, beyond D7 there is no carry, so here carry flag, C flag will be 0, because there is no carry beyond the D7 bit, and the result is obviously it is non-zero, so 0 flag will be 0, because R16 has a value other than 0 after the addition of these two numbers. So here the status of C will be 0, H is 1, and Z is 0. Then again we will see one another example. Show the status of same flag C flag, half carry flag, half carry, and 0 flag. So after the addition of these numbers, now the numbers are different. R20 is load immediate, LDI load immediate, R20 with the contents 0x9c, then R20 is 21 is loaded with 0x65, then addition of this two number 9c and 64, so c is 1100 and 9 is 1001, then 64 6, we are converting into binary this hex number. 6 is 0110, and 4 is 0101, so add this numbers. 0 0 becomes 0, then 0 0, it will be 0, 1 1, it will be 0, but the carry is generated. Now 1 1, it will be 0, but the carry is generated. Again the carry is generating from D3 to D7, so there is a carry from D3 to D7, therefore half carry will become 1. Okay, next H flag will become 1. Next 1 1, this will be 0, but the carry is 1, so 0 0 become 0. Then 1 0, it will be 1, then 1 1, it will be 0, again carry is generating, then 1 0 1, then 1 1 will be 0, carry is generating, then 1 1, the answer will be 0, the carry is generated, and 0 0 will be 0. Now here this carry as it is, so this carry is generating beyond the D7, so carry flag will be 1. So C is equals to 1 because there is a carry beyond D7 bit. Now see this contents of R20. R20 becomes 0 0 without carry, without considering carry, it will be 0 0. So the 0 flag will be 1 because the result R, that is R20, has 0 after the addition. Next, assembler directives. So this is the first directive dot equ, that is equate, which is used to define the constant value or fixed address. Dot eq data is equals to 0x10. That means this data is having value 0x10, so data will be equals to 0x10, and load immediate R20 with this data. So now data is 0x10, therefore R20 get loaded with 0x10. So it is used to define the constant value, or we can say that fixed addresses. So how to address, so it is used for the ramp addressing assignment by this manner. EQU sum is equals to 0x20, sorry 120. So the this assign RAM location to sum. That means whatever the data in sum, it will get loaded to this particular location, that is 0x120. We will see one example. See, first instruction is LDI R20 comma 0x25. That means load immediate R20 with this content 0x25. So R20 becomes 0x25. Then LDI R21 0x15. So the R21 will be equals to 0x15. Add this two number without carry. So R20 plus R21. Then the result will be stored in R20. This result R20, we are moving to this sum. Now this, what is STS? Stored the data. So store STS sum R20. So R20 stored the result in location 0x120. How? Because the sum is already assigned to this particular location. So the result are whatever the data in R20 is get loaded into this particular location, as we have assigned sum to this particular location by using directives dot equ. Okay, next is dot origin, org, that is, this is used to indicate beginning of address. And dot include, this is used to tell AVR assembler to add the contents of the file to our code program. That see, in C, embedded C, we use hash include. So similarly here we have to use dot include. So every program starts with this dot include and org file. So dot include, now we are using, if you are using at mega 16, so use you write m16 def dot inc. And if you are using at mega 32, so instead of 16 you have to write 32, m32 def dot inc. We will see one exam. See, we have already seen this program to blink the LED in C program. So we will try to write this program in assembly language. See, all LEDs are connected to port A. So here port A act as an output port. Port A act as an output port, and the LEDs are connected to port A. Then the anodes are connected to pin, and the cathodes are commonly grounded. So here we use this to uh, hash header files, hash include avr dot avr oblique io dot h, hash include util delay dot h, standard input output file of avr, and this is the delay header file. Then void main program is starting. ddr means data direction register, which is used to configure the port as input or output. Here we have passed the value 0xff, that means it is high, so it will be used as an output port. Then while one, this is a continuous loop, forever loop. Port A is equals to 00, then call the delay, then port A is equals to FF, then call delay. That means one time all LED will glow, and after some time all LED will be off. So this is a blinking of LED program. Now we will write this code in assembly language. See, this is the code. First header file, or we can say directives, dot include m16def dot inc, as I'm using at mega 16, so I'm gonna write m16. If you are using at mega 32, write here m32. Then ldi r16 comma 0x ff, so load ff into r16 and pass this uh, value to port A, because we are here port A act as the output port. For making it output, we have to make it high. So here all pins should be high. So out port A is equals to R16. That means port A will become 0xFF, as 0xFF get loaded into R16, and this the contents of R16 is uh, get loaded into port A. Now port A become output port. Next LDI R17, 0x FF. Now here again out port A is equals to R7 into R17. That means port A will become 0x FF. Now all LED will be on. All LED will glow. Next we have to complement it. So complement R17. So R17 complement of FF will become 0. That FF means 1 1 1 1, then 1 1 1 1 1. This is hex number, and this is the binary representation of FF. So complement of 1 0 0 0 0 0 0 0 0. That means all will be off, all LED will off. So complement it and send that data to port called delay, and then jump to L. Now here called delay. Now this is the subroutine of delay. Delay LDI R20 0, sorry, this will be 0xFF. So 0xFF will get loaded to R20. Then NOP, this is the no operation instruction. So do nothing, then decrement R20 till 00. Then branch. Now this is the branch instruction. If equals to 0, this means if zero flag, if zero flag become 1, then only it will jump to L1. Where is L1? Here. So here if it is, so decrement R20 till it will become 0. As soon as R20 become 0, R20 will be equals to 0, then Z flag will be 1, and then after Z flag is 1, jump to L1 and return to this main program. This is a return function, return to subroutine. So this is the delay subroutine, and this is a program. So you can generate any sequence by passing the values or by loading the values to the registers. Next, addressing modes. So first, the CPU can access the data in different ways. Okay, there are different ways where CPU can access the data, and this data can be in register or memory, which is provided as an immediate values. So this way of representation or various way to access the data are called as addressing modes. So there are different addressing mode of AVR at mega 16: single register, immediate addressing mode, then single addressing mode, direct addressing mode, register indirect addressing mode. Now there are two more addressing mode which is used for especially for at mega 32, that is flash addressing mode or flash direct addressing mode, flash indirect addressing mode. First is single register, that is immediate addressing mode. So in this addressing mode, the operand is contained in register D. Now here this deals with only one register. So this is the instruction increment R18, increment the contents of R18, then decrement the contents of R19, rotate to right, rotate to left, then complement. So these are the instructions which deals with only one register. So this is called single register immediate addressing mode. then single register immediate. So here operands address is contains in 6 bit of instruction words. Now here it deals with two register, rd and rr. Rd is destination register and rr is a source register. So here these are the instruction: add r20 comma r21, then subtract. These two are the instructions which deals with, there are many instructions which deals with two registers, so they are called as single register addressing mode. Now direct addressing mode, so the entire data memory can be accessed using either direct or register indirect addressing mode. Now here the memory location, we are sending the data to memory location, or we are getting the data from memory location. So one instruction LDS, load location 0x560, so the contents of this memory location get loaded to R19. So this is direct addressing mode. Then next one is input output direct addressing mode. Here to access this input output register, there is a special mode called input output direct addressing mode, and one special instruction is used, that is in R16 comma 0x16. So to get the data from input and to send the data to output, out register is out instruction is used, that is out 0x15 R18. That means the contents of R18 will move to 0x15. Next, register indirect addressing mode. Now here in this mode, the register used as a pointer to data memory location in AVR. So here in AVR, there are three register for this purpose: X, Y, Z. They are called indirect register. Hope you have understood instruction set addressing different addressing modes and basic arithmetic and logical programmings.